Okay, cool. Welcome to the Victor Educator webinar. Victor stands for the Volcanology Infrastructure for Computational Tool and Resources, which essentially at its core is a cloud-based platform for volcanologists to find, use, and integrate numerical models and other computational tools. Victor has been funded by the National Science Foundation through the EarthCube and other programs, as well as NASA, all in the US. The motivation for Victor started by kind of really from the community through, for example, reports such as the ERUPT report of the National Academy of Sciences about volcanology, where they highlighted important needs for the community, such as the ability to assess and to have access to high-performance computing and have state-of-the-art models, to have a communal cyber infrastructure that would support databases, model development, benchmarking, and implementation, to have community facilities that would improve the accessibility and user-friendliness of computational approaches, and to enhance the code efficiency and offering resources that are not always available for individual or smaller institutions. So Victor really is ambitious in trying to address all of these needs as they were reported in this report. And it's not the first time that the volcanology community is trying to address these computational needs. We followed the past experience with the VHub platform that many of you maybe have had some experience using. But the thing is that VHub was, very innovative at the time when it started, 15 years ago, but then it became a little unmanageable with things like really limited ability to search and use models. Everything had to go through the developer. Everything was very rigid. It was using a Hub0 technology that was also expensive to maintain. So there's the usage of VHub really declined. It rose rapidly from when it started in 2010, and then kind of dove off after 2015 when the technology just became kind of old, but also that there was no resources allocated through the grants to embedding the use of VHub in the community through teaching and training. And this is really a lesson that we're trying to address is, okay, you build something, how do you make everybody come and use it? And it's not just build it and it will come, because needs to be some skill building and familiarity. So the goals of Victor are to make it easier to run computational models and tools. Higher than that is really to broaden model literacy so that people who are not familiar with modeling, maybe in their undergraduate or high school training, will become more familiar with what models mean, how to be skeptical of models as if you need to. And then overall, the goal is to reduce volcanic hazards by making the models more accessible, making people understand models better. And for people who are, for example, at observatories or at universities or the government, have access to different kind of models so they can really use what they need at different situations. The Victor team includes myself as the PI and Sam Krasnov and Amelia Mullins, who is already also in this webinar. Sam is a software engineer and built Victor from the ground up. Amelia is our education and training coordinator. And then also on the team was Sylvain Charbonnet and Chuck Connor at the University of South Florida, who are the co-investigators, and Abani Patra at Tufts University. A little bit about how Victor came to be. We started with some community discussions around 2019 following the ERUPT report. Then we had a virtual workshop in 2021 about lesson learned and design requirements, kind of like what would a new new VHub would look like in this time. And then the proposed Victor, it got a pilot funded, started building it. Sam was hired 3 years ago. And we had our first workshop with our first users 1 year into the project. We also have an advisory committee that includes people from different branches of volcanology, both academia and government, and both both young and more senior, different types, also different countries. Have people in Italy, Hong Kong, and the US. So really, what is inside Victor? The core piece of it is a hub portal that uses the technology of Jupyter Hub, where users log in and they find large library of models engulfed inside workflows that are either specific to a specific tool or integrated. Then there's a layer of tools, either for visualization or for compiling codes of different languages. And then there's also a way of accessing external data repositories such as Open Topography, Copernicus, and NASA data. If you go on the Victor website, which is listed here, you'll have access to the Hub portal, but also have information such as about workshop and demonstration sessions, who is involved, the people and the committees, as well as access to our signing up for the platform, which uses either GitHub, Microsoft, or Google authentication, so very broad options. We have access to our documentation and our education channels. We'll talk about all of these in a second. I want to mention that there's parallel efforts in the scientific community, such as CSDMS for surface dynamics, Scoped for seismology, ASF Open SAR Lab for analyzing SAR data, Pangeo for oceanography, and Enki for petrology. More details about the platform is that it's running Ubuntu. This is probably a higher version by now. It has fully featured C, C++, Fortran compilers, JavaScript, Python, and R interpreters. There's a variety of Python packages, and it can always be adding more. And it's all hosted on AWS, Amazon Cloud Services, EC2 instances that are managed by Kubernetes. So the sign up, they log in. When a user logs in, they see a screen that looks like that with a login button. Then they get an option to choose what kind of machine. They can choose different, like higher RAM or higher number of CPUs, depending on what the application requires. And then the first thing they would see is that launcher screen. So this launcher screen is that kind of opening screen for the Jupyter Hub. It can, there's a way to launch a graphical desktop, and then also a terminal. So kind of both ends of interfaces as well, which caters to kind of the big range of user experiences and user abilities. And then most of the work is done through Jupyter notebooks. So these are pieces of code that look like that. They combine Markdown, so kind of segments of text, as well as the segments of code. And then the user, either through this button or through a keyboard key, will just run one cell at a time, right? One cell at a time, and everything will be set up for the users. So when a new user comes in, they would copy either through a script or a few sets of copying from the shared folder that is built in and comes for every user into their home folder, whatever model or workflow that they want to use. For example, I copied the IMAX, which is a lava flow model tool, to my home folder. and ran the notebook. And at the end, there's a step of simple visualization. And most of the notebooks kind of look like that, with a first kind of heading of some text, then importing all the needed libraries, then it walks the users through setting up all the different parameters and ending with some visualization. There's also, like I said, a graphical user interface on a desktop that would open a screen like that. So that's where, for example, they would be able to load the results from a simulation into QGIS and make a nicer map with whatever other data the user has uploaded or got from the internet directly to their account on Victor. Like I said, there's a really big set of live models and tools that are already available. Here we categorize by the volcanic process. So we have many different lava flow models, tools for PDCs, ash dispersal, tephra, gas, lahars, slope stability, conduit ascent, as well as more petrological and geochemical tools such as Sulfur X, Alpha Males, Purple X, and Thermobar. And there's new tools and models that are added all the time. The beauty of having a platform where all these different tools are available is that you can go beyond just running one model, which is what you could do on VHub. People could go on and, if it was already set up, run a model online without having to install anything. But now we have all of them installed. And for example, a user can develop a notebook that would run a sequence of different lava flow models at a time, one after the other, which is an example that we already did. So for example, we have a Jupyter notebook that in one notebook starts by setting up common inputs like vent location, DEM, diffusion duration or volume, then sets up specific model parameters for each of the different models, run them all one after the other, and then visualize the results. Like you see here, we're comparing model predictions using 4 different tools for the Mauna Loa 2022 vent location and topography. We have also new capabilities that were not available on VHub, which is access to kind of remote data repositories. For example, here is access to remote sensing data through the Opera project at NASA JPL. Opera provides kind of higher level products. So for example, product for surface displacement that's already quantified. So you don't just get the INSAR fringes, but you actually get quantified displacement and surface velocities. Vertical land motion, same thing. There's a surface disturbance, which usually was used for things like vegetation disturbance for wildfires, but we are using it for example, for lava flow deposits mapping. And surface water extent is maybe less relevant for volcanoes. So for example, we have a Jupyter notebooks where a user can define area of interest. Here, for example, Reykjanes Peninsula in Iceland, get a list of what data is available for that area, pick what they need, and then have an interactive time series of the eruption data, as well as a step that automates the flow footprint detection. For example, one of the Iceland, the Reykjanes eruptions here. So this is something that a lot of students would maybe struggle with, because that would mean going into Earth Data or one of the NASA portals, figuring out how to get the data, downloading the data, knowing what channel they need to access. And this is already kind of tailored for the different applications that volcanologists most commonly would want to do. Another capability that putting all these tools together on a platform is to combine them. For example, running multiple lava flow models and detecting a lava flow footprint from radar data, remote sensing data, and then comparing the performance of all of these models for a benchmark. So for example, we ran Molasses, Mr. Lava Lobo, and IMAX for Mauna Loa, and we got the Mauna Loa footprint from the SAR coherence data. And then we're able to calculate kind of what the true positive, the true negative, the false positive and the false negative, and do a quantitative assessment of all of these models. We're also working on developing inversion workflows where it can feed in observations like tephra layer deposits thicknesses and run a forward model and get estimates on eruption parameters, for example. This, for example, is one of the workflows that we have already developed and have running that uses tephra2 as the forward model. Uses field observations of tephra deposits, run tephra2 forward model, and then estimate things like what was the original plume height and the eruption mass and what their certainty is. So this is an uncertainty of models, and parameter assessment is something that we feel students don't get enough exposure to. They're always kind of give me the answer, what is the answer? And working with some of these tools kind of exposes them to it more gradually and through a real application. We're working on developing a tool for inversion of geodetic data using the D models tool developed at the USGS. Let's get that. And then one of the goals down the line is to really combine a lot of these models to a systematic model tree or kind of pipeline where you can connect a thermal petrological model for the magma chamber evolution, conduit ascent through CONFOR, and then different processes models like lava flows or plume or PDCs and ash and everything would be kind of communicating to each other, even though this is in Fortran, this is in Python, this is in C++, right? I mean, making everything just much more seamless. I mentioned we have a lot of documentation. This is all hosted through Read the Docs, the platform, but it's linked through our website, where you can get information about how to register, how to run models, and then specific documentation and citation information for each of the different tools. We have a lot of training and tutorials that Amelia is going to speak much more about. And then we've also run a full class that is for computational volcanology that uses Victor. This is a screenshot where we showed some of the inversion processes, and that was a class schedule for last year. So you can see we covered a lot of topics, which means we also have recorded lectures on these topics now from these sessions, as well as kind of hands-on activities that we had all our students do. So there's already a variety of content. We run workshops, for example, at meetings such as Cities of Volcanoes, Cascades, AGU, GSA, and other meetings. We just had one a few days ago at IFC, where users would hear about the platform and try different tools themselves. We had a developer summit where people who develop tools came to Columbia University and shared new tools, and now we're digesting some of these new tools onto the platform with the idea of really enhancing the availability, accessibility, and exposure to the community. Coming up next month, we're having a field workshop where we'll combine visiting some of the volcanic features in Snake River Plain in Idaho, as well as modeling in the big classroom facility that the University of South Florida has built in that area. So this is kind of a very general introduction to Victor and what it is and what we already have. And then if there's any questions now, I'll be happy to take them, or we can pass on to Amelia, who will talk more about the educational content that we already have.
I'm Amelia. I am the training and education coordinator on the Victor team. I am also going to share my screen and present a few slides and specifically talk about the content that we have created over the last few months, both on how to use Victor and also how to teach with Victor. So I'm going to walk you through where everything is on the website in both contexts, and then I'm going to introduce a lab example that we created last fall, and Inat is going to walk through the student's perspective on Victor. But before that, I'll show you where you can find the content. The education content is broken up into three main pages. This education menu does look a little bit different right now because we added that computational volcanology class as its own page. So it has 4 menu items if you are following along, victorproject.org, but the meaning of the other pages has not changed, so this will all be the same. This first page, being the For Educators page, is broken up into 2 sections. Each has a slide, not that their content or meeting is totally different, but just for visual recognition. And, once you get there, you know what you're looking for and you're looking at. This first section is the featured educator content section. And the only thing that determines content as featured is that it was either used in a classroom already, and we've received student feedback and made adjustments, or it is just a more complete unit with complementary education materials. Everything that is featured in that first section is also in this all education content section, which breaks up the education content that we've created into topic folders. So there are these expandable, collapsible folders. If you're looking to supplement a certain week or unit in your syllabus, perhaps it would be easier to search by topic. And when I talk about content in this context, we are providing lab assignments, lecture slides, facilitator guides, accompanying answer keys. So that's what you would find in these folders. Also, what is also here is the lecture recordings are also featured here. So when we speak about the computational course, those full hour-ish recordings are here, and those link to YouTube. Almost all of these links are saved as Google Drive documents and are available for download. So when it comes to these units, we usually start with a lab assignment at the core. And if the course has a need or there is time to do so before the lab is distributed and the students run their lab, we will create lecture decks or accompanying materials. And every lab is different, just like every class is different, but every lab does include the procedures for running the target model or models on Victor, and then a case study example that applies what students are learning to a real world context. And we'll look more closely at that when we go through the example at the end. So the training and tutorials section, I also go through, or tab, I will also go through by section, is more of the content, like I said, that's created for how to use Victor and less targeted at the audience of users who are using Victor in the classroom. But I think it's important to point out here, because I think would be a very useful tool for educators to kind of shop around and see what they could supplement, what resources they could use to supplement their education materials, or if they need shorter, smaller content. This first section of this tutorials page, the training tutorials page is called Tutorials in the Menu, is the Victor background. This is content that we use to introduce Victor ourselves, and is generally broader than what would be used in the classroom. But I do want to point out this one resource, which when I was new to the platform, I found very useful, and it covers registering and logging in to the Victor platform. And these procedures are highlighted in labs. So perhaps if students are registering before the day of the lab, so they are ready to begin running their models in class, this would be a good resource to provide them, just for an example of what I'm looking to demonstrate. This second section is called Getting Started with Victor. And these processes are explained procedurally. So written and visual procedures on registering for Victor. There's also a useful functions to know, which either visually demonstrate um, and explain visual cues, such as the cell turning into an asterisk when it's still running. And all of those points, or almost all of those points, were actually put together using feedback from students using the labs in classrooms. And so I'm kind of referring to it as like a quick reference FAQ page. And again, this is always growing, so it will be important to reference it as the page develops. The last section is the topic-specific tutorials library. And this is, just that. It's materials for specific tools on Victor. So a specific video tutorial on running IMEX or Molasses on Victor, hands-on activities in the form of procedural guides. So this example is highlighting a slide that would walk students or users through using Lava 2D on Victor. We have a full webinar on using Thermobar on Victor. So these are very user oriented more generally, but again, could be used to supplement a lab, for example. And I just used this slide to demonstrate that, where the Getting Started with Victor's procedure that exists on the website in the trainings tab is written out on the lab, and we provide the students with a QR code to the Victor YouTube in this example, so they can explore the tutorials on running. This example is Molasses and Lava 2D. So educators are not limited to our For Educators page, is my main point. The final tab here that I have highlighted is just the educator interest form. I know some of you have already filled it out. It just collects a little bit of background on a specific upcoming course, a little background on your students, and then the objective is we reach out to you directly and schedule some time to figure out if we can make what we have on our website, or what is currently being developed perhaps, work for the needs of your classroom, or if we get to do the exciting task of starting from scratch and learning about the specific needs of your students, which is very fun, and we enjoy that task as well. I'm going to just use this time to demonstrate how an educator looking for what will be our example lab, they could find that on our website. So I will point out that this is what the tabs look like now under the education menu with this new computational volcanology course featured. The For Educators page is where we will find the content. So this is a lab that is for the purpose of teaching students, civil engineering students, using Tephra 2. This is in the featured education content section, but we'll go down here just for the demonstration. Here are all the links, and this is the link to the lab assignment, and it opens as a PDF in Google Drive for download. The only thing I will point out before I let Annette walk us through it on Victor is pretty much all the components that are featured in every lab, which are the objectives, which in this case were actually provided by the professor himself for his specific unit, but that's not a requirement. Sometimes we create labs and come up with the learning objectives, but in this case we kind of aligned what we put together to his objectives. This prep and materials, which ideally we prefer to have all students registered before, but just in case, all this information is provided here. Along with, like I mentioned, links to YouTube, tutorials that we've created, background readings. For example, here is the Tephra 2 user manual. And then from here on, the task and procedures is where it becomes more specific for every lab. What will be included though is, of course, installing installing the models for the specific models required for the lab. So in this case, it's one model and it's Tephra 2. But other than that, the procedures and the analysis sections are specific to the lab and the learning goals provided by the professor and the topic. So I think Anat's going to walk through on Victor the more specific components of this lab. We can't hear you. Sorry.
Sorry. Okay. Are you able to see both my PDF open and my Victor hub?
Yes.
Yes, okay, great. Okay, so here, for example, is a situation that a student could be working with. They will open the lab instructions or get handed those from that menu of lab information, just like Amelia showed, and they'll see the instructions. So the first instruction for them would be to sign in, to sign up for the platform, and then sign in. For this specific lab, it deals with a hypothetical eruption from South Sister volcano in the Cascades. The students are instructed, for example, to pick 3 buildings in towns nearby. And they can do that with Google Maps or Google Earth, and then find the location of these houses, the roof area, and the type of the building. Like Amelia said, it was designed for kind of more applied engineering application. And then they get in, and the first thing they're going to do is from the launcher screen, they'll click terminal and run a script called Victor install. Oh, sorry, Victor setup. Change the name. And for this lab, they're dealing with Tephra 2, so that is number 18. I'll choose that. And then it'll format, it'll create a folder for them called Tephra 2 and guide them to go in there and open the Jupyter Notebook. Then they'll follow along and be able to run the different cells. And the lab will show them where and when they need to make any sort of changes. For example, set up the date for which they can obtain wind data from the Copernicus site. So for example, if I run this notebook myself, the first few steps, then here they can add the location of the volcano. Right now it's already set up to South Sister, but if you wanted a different volcano, this is where the students will change it. Very simply, they can add latitude and longitude for their own interested volcano. Have set up some parameters for the eruption, get the DEM for that site, and all they have to do, they don't have to go anywhere. Everything is using the Victor library that comes with their installation, and there's a function called download DEM, and it just uses the location that they entered. So if they're changing a volcano, it's all flexible and done within. Then they'll input some of the eruption parameters, for example, the plume height, the eruption mass. These can be done based on, for example, parameters you provide to the students in the notebook, in the instructions. Then there's some kind of formatting that the notebook just does for them. So they don't have to, like they used to be, if you wanted to expose students to models, you have to go with them through installing, getting libraries, getting the dependencies, making sure they know how to deal with the input, the output, and all that. And that just kind of takes out all the fun. Here they click through the not interesting parts. Here, for example, is they would put in the coordinates for the buildings that they just picked themselves. So the instructions would tell them how to do that. Then they'll click in the WIN file that tells them they put in what dates of an eruption they want to do. It needs to be in the past because we're using historical weather data. And then again, it will set all of it up for them. So it grabs the data from Copernicus using this functionality of retrieving data. And then they don't have to worry about how do I get in, where do I find it, what kind of parameters I have to put in the whatever portal, whichever agency is using. That may be taking a few seconds. Then they get to the exciting part of actually running the model using all the information that we put so far. And then they're told that this can take a little bit of time, so they should be patient. Because I already run it, this is the output that they will see. And then specifically for the coordinates that I entered as parameters, but a student can change based on their choices of buildings, for example, they get the output. So that would be, they can run, in this lab, they're asked to run with different erupted masses and see on each site with the different volumes and masses, what was the deposit mass per unit area and load and the total mass on the roof. Because it's engineers, they wanted to also know where will this building collapse. So we provided them some information about different types of building and what kind of load would lead to collapse. So then they had to decide, on for different eruption volume, will specific buildings that are real and next to a real volcano would collapse. Again, a very practical example. We also have labs that are a lot more theoretical, maybe dealing with thermobarometry of samples from a specific volcano or different database that maybe this you have and want to use. Wanted to show another lab that we have, for example, is for lava flows that goes through similar process. There's a little bit of background. This is for the Mauna Loa 2022 eruption. Students get familiar with the area, a little bit about the eruption. That's the map of it. Then the general instructions of, again, going again to the terminal, doing Richter setup, and installing, in this case, molasses, which is a lava flow cellular automata model. And then they would be guided to go into the molasses folder, open the notebook, and everything will be set up for them with importing all the libraries that they might need. Everything is already included. Setting up the key parameters, in this case, we already have the DEM for this case, so it doesn't need to get downloaded. Setting up the events, and the students have to run the model, look at what happens, for example, when they change the eruption volume, what is the final flow length, and how long it still has to go. before it goes to the saddle road that crosses the island of Hawaii. Then there's a discussion what eruption volume, based on the 3 that they are asked to run in the assignment. And then they plot this data. So again, practicing data processing and speculation and then inferences. What kind of eruption volume would lead to the lava to cross the road? So there's have a level of discussion. In this specific lab assignment, there's also another type of lava model that they're running and they could run that's based on a different mathematical approach. And then questioning about comparing the different models after you go through the same analysis. What have you learned about using models? How would you trust the model more or less in different situations? So like we said, there's the goal of increasing model literacy and not just teaching specific skill of how to use a specific model. So this is just a couple of examples of our more popular labs. There's, like I said, a large set that is being developed and some already exist. And we'll be very happy to work with any of you to develop more content. I also wanted to mention that this summer we're working with a Spanish-speaking student to translate a lot of our labs into Spanish, in case that is relevant to some of your students.